momentarily. Now we are. Let me make sure I can share your screen.
Well, his technology just got me back.
Brad won't be talking to you. He's just talking to you.
All right. Let's see if we can share your screen real quick.
All right. Let me do my share right here. Let me oh, it says you disabled participant screen sharing. I'm going to share my presentation.
Try that one.
And let's see. This is
There you go.
okay. You can see it. All right, cool.
Okay. You want to give us an
All right.
introduction, please, Brad?
Yeah, totally. Yeah. Hey, hi guys. My name is Brad White. I'm an engineer. I live in Boston or near Boston, and been doing this for about 40 some odd years. Part of my duties here, I work for a company called Arup, which is probably best known as, I think if you think of the Sydney Opera House in Australia with those nested shells, that was actually done by the founder of our firm. He was a structural engineer, but I'm the mechanical lead up here in Boston. And one of my duties or habits in this is teaching, and I've been teaching Boston Architectural College and a few other places, mostly teaching for architects. So I'm teaching to people that are not going to become engineers necessarily, but I also teach and groom my own engineers as well. And I found that this is just the presentation I'm about to give you, just to give you a little sense of this, is maybe too basic. You probably know 80, 90% of it, even 110% of it, and that's okay. So I do it for a wide audience. I get a little technical, or I can just be high level, and it's really more about conveying information in a way that that hopefully people find interesting or informative or reinforcing or whatever. But I would like to get your comments after we're done, and during as well. Uh, sorry, been a long day. So I'm just going to get right into it. This presentation I did about a year ago for in-house consumption, but I want to just do this as a, oops, sorry. My controls are not quite reacting. I'm sorry about that. I do apologize. Okay. Can you see the slideshow?
See the first slide.
The first slide. Okay. And second?
We can see the menu bar on the left side with all the slides on it.
Yeah. Oh, this is just, it was working well before, but let me just get this.
That's fine.
This is right here. Okay. Well, anyway, get right into it. Sorry for the rough start. This is, I call it Psychometrics 101. It's a very short foundations course, as it said, but it's also just to get people familiar with it, with the concept. Here I give a very brief definition, but the most important part I want to convey are the 4 takeaways. You can see all the takeaways, right?
Yes.
Okay. Yeah, I want everyone to understand, how to read the chart. You probably already know this, and if you do, that's a-okay. Know how to read a chart, how to know the relationships between moisture and variable conditions, what happens at what level, understanding what happens, how to control it, and how to control humidity and air, and how to alleviate it or add it. And above all, the bottom part is be comfortable with finding answers to your own questions. I'd ask for a show of hands. Unfortunately, I can't see everyone here because it's very small screen at this point. But I just want to get a sense of most of you have some basic background or maybe even more advanced background in psychrometrics. You probably have read more psychrometers than most people I know. This is more about the science, but also more about the general principles of this. And if it's too basic, I apologize. These are the basic terms we're going to be using. You've heard the term dry bulb, wet bulb, and I'm going to show you how those are derived. Enthalpy, total heat content, relative humidity. We know that it's the most misused term in engineering and HVAC engineering. It's, oh wow, it's X relative humidity, which is of course meaningless without temperature. Absolute humidity, that's we're getting somewhere there. Sensible heat ratio for selecting your equipment and just for understanding the capacity of your equipment. Saturation point, and we have the tools hygrometer, sling psychrometer. And a little out of place here is state point, which is a fixed condition of air. This, I don't know if I have, have these been used in some years. Mine is just about retired at this point, but I've got one of these that's been handed down to me by my dad. And the wet bulb, of course, has to do with literally a wet bulb. It is twirled in the air and it evaporates the air around this thermometer, cools this down enough so that if it's very dry, you'll have a lot of evaporation. And this wet bulb will have a lower temperature than the dry bulb, which is measuring the straight, warmer air temperature. And you'll get a difference in temperature. And you'll normally read these at, if it's 75 dry bulb and 62 wet bulb, you'll get that's the smaller temperature. It just tells you how moist or how dry the air is. Your basic psych chart. And I tell people, don't be afraid of this thing. It's not, it actually can be one of your best friends if you really have a problem trying to troubleshoot a unit or a system or what's going on in a building when you've got a lot of moisture, condensation, mold growth, perhaps. Maybe it's too dry and you've got static electricity. You take a few readings and you can get a handle on how this building is performing. This psych chart, this is the basic concept. It's warmer and drier over here on the right side. It's colder and drier on the lower left side. As you move up the chart, it gets more humid and somewhere in between. And over here on this portion is the saturation curve, where I call it foggy. And this is a fairly limited range of temperature. The charts can actually go all the way down to minus way below zero and can go actually up over 400 degrees if you're doing turbine work. So this is just one snapshot, one type of chart. They're very flexible and they cover pretty much the entire variety of air you're likely to encounter. And every point in this chart has a certain property. And one of the things I ask my students to do is I call it the dartboard test. To take as part of your quizzing, you take a push pin and you push it anywhere in that chart. Just drop a pin here, drop pin here or here or here, anywhere, just blindly, and tell me everything about that point. You can tell me the density of the air at that point. You can tell me what the total heat content is. You can tell me the temperature, the relative humidity, the absolute humidity, and as well as the as I mentioned, the weight, and where its dew point is. What temperature is it going to? Is that moisture in that air going to condense? So again, any factor you want to know, it's on this chart. It's embedded in this, and that's why these things are kind of are very useful. Dry bulb, as the name implies, is strictly reading of the dry bulb of a thermometer. The scale of this is along the bottom. The temperature goes generally colder, always colder to the right, warmer, sort of colder to the left, warmer as you go towards the right. And the lines that index to this scale are vertical lines. So it's a horizontal scale, vertical lines. And they all end at the top at what's called the saturation curve. This is the point where no more moisture can be suspended in the air and it will condense. There's no air outside of this line with moisture in it. And then there's wet bulb. Wet bulb runs diagonally. And these are constant lines. So it happens at all different temperatures, and they also end at the saturation line. And what you'll notice is the dry bulb lines shown here in red, when they intersect the wet bulb lines in blue at the same temperature, that's 100%. When those numbers are equal, the air is saturated. Wet bulb and dry bulb are equal. If it's so humid out that wet bulb on the hygrometer can't evaporate. There's no evaporation taking place. Both thermometers are going to read the same temperature. So there's dew point. Any point on this chart, if I go straight to the left and I hit that saturation point, that will intersect with a dry bulb temperature, and that'll tell you at what temperature that will condense. So if you've got, your proverbial warm glass of iced tea or beer, and you're outside on a hot summer day, and that beer is 42 degrees, you could say, well, I'm going to condense at a fairly cold temperature. It'll condense at, anything higher than your temperature, it will condense. You'll just get beads of moisture on your beer, and that's pretty much the end of it. But it just gives you an indication. That's useful for understanding how a cooling coil works. Cooling coil has to be at your dew point or below to remove any moisture. Then we have enthalpy. This is the part that I think most people get really kind of, they don't quite as understand it as much in general terms, especially when I'm teaching architects. But this is the total heat content of air. So it's the sum of moisture, temperature, and in any combination, but it's a constant value. So I can have with these enthalpy lines, you can see these enthalpy lines, the blue ones, very much like and very parallel to the wet bulb lines. The two are almost parallel. And I'll have the same moisture content down here on the right side, on the lower right side, as I will up here on the left side. This will be more humid. This will be drier, but it's warmer, but it's the same total heat content, just a different ratio of moisture. And as far as total energy, it's all in there. It's exactly the same. Now, relative humidity, again, the most misused term in HVAC engineering and discussion of this is how close are you to saturation at a given temperature? If I'm at a given temperature and there's X amount of moisture in there and I'm at 50%, 50% means I'm halfway to saturation. If I double my moisture, I'll be saturated. If I drop it to zero, well, I'll be at zero. And the way these lines, these relative humidity lines are these curves. You can see these curves running from the lower left, sweeping up to the upper right. I think you can all see those curves. And the way these curves were derived is these red lines. Here's a typical temperature line drawn from the index up to the saturation line. Those are divided into 10 equal parts. The next line is also divided into 10 equal parts and 10 equal parts and so on. All those little tick marks you just made, you connect those dots, and now you're drawing a curve. That's how those curves were derived. And they sweep all the way up and they stop at 100%, 100%, 90%, 80%, and so forth, and infinite numbers in between. 10 is just a very convenient number. Absolute humidity. This is the more meaningful part. How much moisture in mass is actually suspended in the air? It's often used in terms of grains per pound. That's what I like to use. That's how I learned. But pounds per pound is another way to phrase this. A grain is 1/7,000th of a pound. There are 7,000 grains in a pound. And I find that more useful instead of a multi-digit number like 0.0036 pounds per pound. To me, just tell me 24 grains per pound. It's a lot more tangible to me anyway. Use the term you're comfortable with. Those grains per pound are read down here on the right-hand scale of the psych chart. And from there, you can read straight across. And that will just, any line that's directly horizontal is same temperature. I'm sorry, different temperature, but more or less humidity. More humidity, same amount of humidity. Can't even talk. The higher these bars are, the more humidity. But these are all at a constant temperature. These are constant temperature lines. Now we have specific volume and mass. This is useful if you're going to be calculating CFM. CFM is great. We have got all sorts of shorthand terms we use, 1.08 or whatever. We have certain multipliers we use when we're doing our calculations for enthalpy or for cooling loads. But what I do with mass is I actually will calculate what the actual temperature is, what the actual mass of the air is. It's more accurate. And if you're working with very cold air, if you're doing something that's -20, it's important that you actually use the mass of air because you'll take a cubic foot of air, but you're going to find that it weighs a lot more. It's more pounds. So your calculations will be a little bit short if you use those rules of thumb type constant numbers. And I have this cold air caution. I'm going to show this over here. This is, and by the way, these handouts, I gave a PDF to Tom to distribute to you all. So this is something you can refer to later. I'm going to give you this cold air caution over here. This cold air caution is what I was getting at. At -10, the density of air is 11.3 pounds a cubic foot, which doesn't really mean much unless you have a scale, but at room temperature, 70-ish degrees, it's 13 pounds. So it's something 13.5 pounds, 13.5 cubic feet per pound, rather. So cold air is about 18% heavier when you're talking about, climactic air. So the operational takeaways, this I give to my engineers as well. One of the things I find that a lot of engineers and some installers, it's, everyone knows what they know, they practice what they know, and we all share from each other with each other. But what I found is that a lot of air conditioning systems where there are muggy conditions, there's humidity, there's mold on the walls, or paper starts to curl in the paper machines. The first thing I look for was the coil designed to get the air below the dew point, significantly below the dew point of the air, so that it has room to absorb the moisture that's generated within the space, or comes in with ventilation, or comes in with from any source. It's be it a swimming pool, open tanks, or just a lot of people breathing. It's a lot of moisture to deal with. So what I always seek is, are we coming off the cooling coil in the low 50s, 52, 51, 50? That's a start, assuming you're trying to keep 75 degrees or 72 degrees in a space and about 50% relative humidity. If you come off a cooling coil at 58, 59, 60, you can't dehumidify anything you can call comfortable in a normal conditioned space that we're used to having. What I also find is that if you're doing a performing arts center or a museum or a conference center where you've got a lot of people in one space, you have to get that air a lot colder. You probably have to get it down below 47, sometimes below 45 to get the moisture out of that air. Costs a lot of money. It's kind of expensive to go chasing humidity, but the energy cost is worth it if that gives you what the space is needed, the space requirements are. And you'll also find that your typical fan is going to, especially if you do blow through, if you do a draw through system where the cooling coil's first, then you follow with a fan, that fan is going to add a few degrees of heat. We all talk about fan heat. We can quantify it a little more easily, but you're typically going to get between 1 and 3 degrees of heat off of your fan. It's not just motor heat, the heat of compression, just like a diesel engine piston compresses and raises the temperature, so too does do fans when they compress the air into a duct. So we cool it down to 52, we get free reheat. We put it into the space at about 55 degrees. And that's what most people find reasonably comfortable for typical air conditioning. I'm talking about comfort air conditioning, not talking about particular processes. But it's important you buy the coil once, make sure the capacity is built into that coil. There aren't a whole lot of things you can do once the coil's built and installed. You're pretty well done. Oops. This is more for my engineers, but I tell them to check the computer-based calculations manually. A lot of times there's a tendency when a computer program tells you an answer, you need a point of reference. What does it mean? Is it a good number, a bad number? And that's why I go back and say, look what the temperatures are. If it tells you, yes, I can cool a space with 60-degree air, but I can't dehumidify it. You know, VRF systems, I think you're all familiar with those. They don't dehumidify worth a darn. And they will dehumidify by accident or on occasion, but they're not going to be targeting humidity without extensive controls. They're not really made to do that. They just want to take the temperature down, but they tend not to remove humidity unless it's already muggy in the space. So that's why I want to get that air down, again, below 55, 50 if I can. And I tell them about the different kinds of humidity loads, whether it's in the space, and people, animals, and so forth, what's in the unit, what's in the space. This is more for designers. And if you have an answer, I can go into more, a question on this one, I can go to more detail.
I have a question.
Please, yeah.
So is that 50-degree discharge air we're trying to get to?
Generally 55. What we're looking for is 50 off the cooling coil.
So that would be the air immediately off the coil.
Off the coil, correct.
12 inch. Okay. So where's that put refrigeration process? Where's that put my coil temperature at?
That coil temperature is going to be in the range of, it depends on the refrigerant, but you're going to be about 40 to 42 degrees.
So you only have an 8-degree split across that design coil?
Correct. Yeah, with a typical, well, let's put it this way. With a chilled water coil, if you're using 42 or 44 degree chilled water, and obviously reverse flow, you can do it with 40, 42 or 44 degree chilled water and a 12 or a 14 degree delta T. With refrigerant, your cooling coil temperature, your saturated suction temperature is going to be somewhere down around 40, maybe a little lower.
It's still 10 to 12 degrees.
Yeah.
Typically
Correct.
we see 18 degrees.
How much? 18?
410A, right? 18 with R22 if our airflow is correct, or if the statics by design.
You're getting that low? I mean, below your discharge temperature?
R22 coil. That's how we check them. 18 degrees, fly to return. If I'm 72 degrees, I'm looking for 58 degrees at my diffuser for standard, air conditioning coil, not a dehumidification Lennox, or not a Liebert unit or something with different fin space, but basic air conditioning is 18 degrees, isn't it, Tom?
It depends on humidity. What Brian was relating before about the humidity, if we got a high humidity, your delta is gonna be lower. If you got drier air, it's gonna be higher.
As much as the 5 degrees, you think? 5 to 6,
Oh, yeah.
8 degrees?
Yeah. That's what the measure quick does for you when you're looking at that. It calculates it all. Pretty cool in that respect. But that's on the air split, talking about draw through. Or yeah, you're talking about a draw through coil on this, and you're picking up fan heat too, which we really don't calculate into anything if we're measuring.
Well, you get motor heat from a push through as well.
Right. Except that if your coil is colder, your motor's on the draw through side, right? The sucking it through that, the
Yep.
motor's gonna reheat. Right, okay. If it's on the flow through side, it's gonna add it to the coil. So you got an accurate coil discharge temperature that way, right? Going into the duct. Sorry, Brad.
No, that's good. No, I would know this is good. It's good discussion. And one thing I found about blow through coils, and I've used both up here in the Northeast, we use draw through almost exclusively. And package equipment, you get blow through sometimes by default. That's just how they make them. But I've used draw through probably 90% of the projects I've ever, 99% of the projects I've ever done. The only ones I've ever used blow through were in the Southwest or in Colorado, where it's relatively dry and dehumidification is not much of a concern. They want to add that heat to the coil. And so and they don't need to get it down that cold because they're not removing as much moisture. So they'll come into the coil, the air will come back at, let's just say it's coming back to the unit at 78 degrees, goes through the fan, it might come off at 80 degrees, and they'll cool that down to 56, 57, 58, whatever's needed to cool the room. But it's not going to remove humidity because you don't really want to. there's no real need to, and there's no humidity to be removed to begin with. So they don't have a need to subcool it. But up here, and especially say in Florida or the Gulf Coast down in Texas, where you've got an 80-degree wet bulb and it's thick, the air is thick. They actually run actually two-stage. Sometimes they use two-stage cooling coils. They do a first stage, a second stage, often on completely separate circuits, and they'll trim it with a second one. But they'll get that air down to 39 degrees sometimes, and they really dry it out. This is for DOAS units and so forth, because they're trying to protect the building and manage their outside air through a DOAS unit. And that's where you really take a hard look at how much you're conditioning, how much energy you're spending to condition your outside air. And most of their units inside the buildings, in Florida in particular, and in Houston, for example, are recirc units, almost like a giant fan coil unit. But they bring the outside air in, they wring it out, and that's the agent of dehumidification for that space. The recirculation unit will dehumidify, but the DOAS unit will really dry that out. It'll take it down to somewhere in the 30, 39, 40 degree dew point. And this is without desiccants. I'm just talking refrigerant process here, not talking desiccants. That gets, down to minus 15 if you really wanted it to. Well, this process, I call it, is wringing out the sponge. I'm just going to flip through these. These are not, I think we're all in the same relative sense of experience on this. Sorry, all right. No, sorry, this is a little out of order. My apologies. I want to talk about the process of adding air and subtracting it. And that's what this is all about. How do we do it? How do we figure it out? And how we generate humidity, why it's expensive, and why too much in winter, if you do it with a heavy hand, you can actually drive moisture into your structure and cause all kinds of rot and other problems and condensation inside your walls where you can't see it. And low humidity, I don't know how much you humidify outside of a medical application, for example, or maybe you have a factory process like paper making or a mill or something where you want to keep dust down or static electricity down. But I'd say very few places, certainly very few homes have humidification, at least in our climates, even in the real cold ones. So we reserve that for the, obviously the medical profession, the medical areas. Now, one of the conversations I do a lot of performing arts centers, and I've had this one person who was a piano expert, and he claimed that you could never have a piano at lower than 20% RH because it would crack. And I said, well, it's not the relative humidity, it's the rate of change. If you go from 50% to 20% in an hour, that's going to put stress on all kinds of hygroscopic materials, wood, paper, whatever. It's going to stretch, it's going to break. And finally, I just told him, are you telling me that there are no pianos in Arizona? And he said, of course there are. Well, that's what I'm saying. So that's kind of one of those little, wasn't meant to be a snarky comment to the guy, but it was just one of those things that came out in the moment. It's not relative humidity, it's the rate of change. That goes for your nasal passages as well. That's why when people come into a warm, humid room and go into a cold, dry room or a cold, dry space or go outside, they tend to get nosebleeds. People's mucosa act differently. And you wind up with cracked skin, bleeding nose, sometimes have bleeding gums, depending on how cold it is. It's all about rate of change. Here's the dull part, the formulas. And I put these in to your handouts in case you ever needed them or wanted to know how they were broken out. Now, those of you that done the calculations, whether by hand or on worksheets or whatever, you've seen the formulas, 0.68 is a multiplier for humidity for enthalpy, and 1.08 or 1.085 for CFM, temperature times 1.085 to get your CFM. And I wanted to just explain in more detail how those are based or what those are based upon, where those numbers come from. It has to do with the pounds of air that you're moving, the specific heat of air, which is 0.24 BTUs per pound will change it 1 degree. And 60 minutes per hour because we're dealing with everything on an hourly basis, cubic feet per minute, but we talk about it on an hourly basis for heat transfer. So this explains how the 1.08 factor is derived and where that comes from. And these are shortcuts on enthalpy. This has to do with the total heat content of air and how that's broken down. I'm not going to read it to you. I'll let you read that on your own, but it's all in here. And this just gives you a range of, for normal air conditioning temperatures, how to get the actual amount of total heat you're going to be removing based on how much air and how dry it is or how moist it is, what the percentage is. Mixed air, you have multiple processes. You'll have energy recovery thrown into the mix. You'll take a lot of that energy out and you wind up with 2 or 3 airstreams mixing together. And you have to figure out, well, I'm going to take this mixed airstream, how well mixed, bring it through a cooling coil, bring it through filters, bring it through all the process and out into the space. And this is just to break it down into a smaller chunk where you can say, oh, that's where these numbers come from. And then the practical side, this is, okay, we get a sense of, I hope, a sense of, how proportions of air and moisture interact with one another, how to measure them, how to work with those numbers. And then it comes to, what do you want to do with it? What do you want to do with this information? And you might find yourself having to dry out a space, and you look at the amount of moisture being produced in the space. And I use people load, people breathing in a space. I do a lot of airport work or passenger waiting areas in a railroad terminal, for example, or an art museum where things have to be kept to a certain dryness. You've got lots of people coming in and going out, and ventilation air, so forth. So just want to get you a sense of how you would use differences in temperature to change the heat content of the air. If you say, I've got X amount of air to move to heat a space, and it's coming in at 80 degrees, and you find I need more heat. Well, the only option you have, if either you increase the volume of air, which you can't always do, but you also have to increase the temperature of the air. Likewise with moisture, if you've got an air off a cooling coil at a certain absolute humidity rate, a certain number of grains per pound, and you want to dehumidify a space with a lot of people in it, you're going to have to add either a lot more air or take the same amount of air and dry it down to a lower grains per pound. So you've got a greater delta. It's like delta T, delta temperature for heat, delta grains for humidity. It's the same process. You're moving massive air through a space at a difference in humidity and or temperature. And I'm not going to read these slides because that would just be cruel. Here's a sample of removing humidity from a space. You have your space, what things you need to know: your space design target conditions, your space discharge air conditions, difference between the two, your available airflow, I call it mass flow, but it's airflow, and your gains in BTUs or grains per pound per hour. And I give you here's a problem, and I'll let you take a look at these in the handouts as well. But it breaks it down line by line how it's figured out what the delta grains per pound is. That's the problem. And then there's one solution is you have to move so many pounds of air per hour, how you multiply it out. And now you have your delta grains per pound. And you wind up with so many pounds per hour you're trying to remove, so many pounds of air you're moving, divided by 60, and that gives you your airflow rate, 649, call it 650 CFM. Now, this is more for my designers and engineers, but I think as contractors, you might find this handy as a back check. Now, if you want to add humidity, again, it goes down to delta grains. I've got a space at 72 and 30% RH. I want to keep it at 32% RH. I'm bringing in 1,000 CFM of cold outside air. And I'm going to assume 0 grains moisture because that's a pretty fair assumption. And I always throw in 25% surplus for diffusion just because you're not just taking outside air, but you also have infiltration and other forces of vapor pressure pushing the moisture out into the colder, drier outside air. And I break down the problem, the solution, the calculations. Pretty straightforward. It's pretty much straight math. And it just gives you an idea of, okay, you're going to size a humidifier for a musical instrument storage room, or maybe it's a nursery or someplace that requires a certain amount of humidity. And this is how you can go about calculating it, getting your sizes, and understanding where the loads and where the numbers come from. There are lots of programs that will do this for you automatically, but this gets into more not into the weeds so much as into the real what's underneath the hood. So you don't always have to trust your programs. I always have my engineers do their calculations by hand so that they don't have to. They have at least a benchmark, a mental benchmark of what a value is. Oh, this is how many BTUs it takes to heat a room about this size. They get a mental image and bring that into their DNA. And that I think gives them a better, better framework, and not to guess, but rather just a point of reference that, oh, that seems like like a lot of heat for that size room, or that's really not nearly enough, or airflow, or whatever the question is. And that is the presentation. And I'm totally open to questions or suggestions or anything else. I'm sorry for the rough start.
So I don't know if this is part of it or not, but can you explain vapor pressure depression?
Vapor pressure depression?
Yes.
Well, I could explain vapor pressure. Certainly, vapor pressure is the well, let's see. I could show that on the psych chart. Actually, I don't know if the psych chart actually has that.
One more.
I want to get the clean one. I want to get one with a little more grain in this one too. But yeah, the vapor pressure that has to do with the vapor pressure is based on absolute pressure of. Oh, I knew you were going to do this to me. Thanks, Tom. No.
Well, tell you how
But
this came about.
What's that?
This came about because of a humidor sensor that I have. And it logs the temperature and relative humidity and vapor pressure. And it's measured in kPa, which
It's supposed to inches mercury.
What's that?
As opposed to inches mercury. Yeah, but it's the same. Yeah.
Yeah. So I'm trying to understand the relationship between the three items.
I'd have to do a unit conversion for kPa to inches mercury. But I mean, the vapor pressure is the motive force that drives moisture from one way to another, irrespective of airflow. So if I've got a surface of a wall, for example, or it's the boundary of a humidor, or a dividing point between two areas of grossly different or measurably different humidity ratios, the vapor pressure difference measured in those finite units is the motive force. I can have airflow going in one direction and vapor pressure will go in the other. There are factors that bear on one another, just like gravity works regardless of, you're falling, the level bullet in flight is going to fall at the same rate. Just because it's going horizontally doesn't mean it doesn't drop. That rate is the same. It's just another factor acting on the object. And I found vapor. So sorry, Ed.
So the vapor pressure is driven, it will change with the temperature then and drive the moisture, whichever way it's going to drive it.
It changes more with moisture. As I recall, changes more with the quantity of moisture in the air, and less so with temperature. But I've got the gradient on that. Actually, I have a gradient calculator on that. And here we go. We're flying on a calculator. I'm not going to bore you with that. But I believe that's more of a function of the total amount of moisture in the air as opposed to temperature. Temperature is a factor, but the amount of the moisture present in the air is what's driving it. Because it doesn't,
Right.
because the temperature is not going to change the amount of moisture in the air.
Right. I was thinking about it more on a global type thing after I realized this, and oceans and low pressures and all that kind of thing. So, I'll shut up now.
No, it's a good question. No, it's if I could think about that, you go, yeah, okay, it's straight across. It's a humidity based line. I only use that when I'm doing Wolfie or something, which is, that's that program that does the migration of moisture across walls and such.
Well, when Brad and I were discussing this, anybody have any questions on a site? Psycrometric? One of the items that we discussed was how much things in the last 3 years have changed for him on an engineering perspective with DOE standards and supply chain.
From the engineering side,
Yes.
we're at the beck and call of what you guys can build and what you guys can find. What we've been specifying, I mean, most everything we specified has been obviously delayed and it's coming back, but it pretty well put a stop to most projects. People just didn't know what to do. They just locked up. Then the DOE stuff, we're getting hit with that in Massachusetts now because what happened, we're phasing out R410A faster than other states, and other states are joining it too. They're joining in the bandwagon. And we've had projects that were ready to bid late last year and early this year. And they're all R410A, which for heat pumps is not a problem, but after another 10 days, we're not going to be able to build them, to install them in Massachusetts. So if you're using R410A for a chiller, it's a no-go. Same thing for regular rooftop units, small package units, and so forth. And with all these projects that were bid or about to be bid, the manufacturer said, we can't get all the components. We need to have all the components on the floor before we can build the unit and commit to a construction slot. This is for packaged stuff that used to be stock. I'm talking 5, 7.5, 10, 12-ton rooftop or on-grade package equipment. And they can't get a controller or they can't get a starter. There's something made in Saudi Arabia that they can't get. And it would take more time to get that one component. And also, if they had to get a substitution, they'd have to have all ETL and UL listings redone, which is not, you don't want to do that for packaged equipment. That's a commodity. So they canceled orders wholesale. Whole categories of equipment were taken off the market because there was no guarantee, not even a prayer that they could get the equipment built, manufactured, built, and delivered and installed, because that's the key phrase of that phase out, by December 31st of this year. So as of April, they were just saying, your unit that you were just approved the shop drawings on, well, it can't be built. It won't be built. Lead times for one component would throw the whole thing out of whack. Now that's maybe, ambitious use of, trying to get refrigerants banned, but it put a dent in the industry for sure. And already some of the units that they have are still sitting in the yards and they're going to be scrapped.
Let us know what they are.
What they are, what they are?
Still use them.
I couldn't hear that. What?
We can still use them instead of scrap them.
Can you use them in Ohio?
Yes.
Yeah.
This is great. This is great.
Capacity magazines.
Yes.
Girls too, send girls.
I'm glad someplace can use them because we've got a whole bunch. We have a whole project now where the equipment was pre-purchased a year and a half ago, but it can't be installed now. So they're going to put it out on the market or scrap it or something. I don't know what they're going to do, but there's a discussion happening in more in political circles here in Massachusetts about not selling them on the open market. It's like contraband. And these are state owned. It's a state owned building. They'd rather scrap it than sell it to someone who could actually use it. It's part of a circular conversation we're having. Like, where can you, I hate to waste it, but we can't use this equipment here. So what do we do? And I mean, again, it's their problem, but it's our problem. I'm a taxpayer. I bought some of this. But they were like, no, we can't. We've got to dispose of it in a lawful manner, which means they have to capture the refrigerant. I don't know what they do with it. You can't sell it anymore. I mean, I guess you could sell for heat pumps and stuff, but pull the POE out of the compressors and, clean them out and send them to a scrapyard or something, or send them to states with a little more tolerance for this.
We'll open a museum. How's that?
Yeah. Smithsonian.
Yeah. You can borrow it for 20 years.
I mean, we're speccing a lot of air source heat pumps. That was our saving grace because heat pumps R410A is great for heat pumps because there's no real substitution for them now. They don't have a plan B for that. And everyone loves heat pumps, as you know. But what they found is that, or the ruling they gave us is these heat pumps are air to water. They make hot water, low temp hot water, and reasonable chilled water, 42, 44 degree chilled water, and 110 to 130 degree hot water. So you can work with that. But because it makes chilled water, they didn't want people to use it as a substitute for a air-cooled chiller. Forget the heat part. Now it's an air-cooled chiller. They saw through that and said, well, now you're using it as a chiller. It's not considered a heat pump anymore. So therefore, we cannot use R410A in that model. So those get scrapped. And now they're all using R455B. 455B, was it? Yeah. And so, here we are. So we're waiting for new product to come out that fits in these capacities that we can use and specify. What are you guys seeing?
Lead times are incredible on some pieces of equipment. We had a chiller that was slated to be on the ground here in September, and then they said November, and 2 weeks later they said mid-March, right?
Wow.
March.
What brand is that?
There'll be a trainer over there saying, no?
No.
Carrier?
Go ahead.
Carrier makes sense.
No, it's not. It's whatever the Johnson Controls product is. I can't think
That's
of the
York.
name.
That's a York. That's York.
Well, it's not York anymore.
No, but JCI and York are joined at the hip anyway because they're owned by they're mutually owned.
It's a decent chiller. We've had zero problems with them.
These are the ones made down in San Antonio. You talking water cooled? How big?
Well, air cooled.
Air cooled?
Yeah, this particular one was a 70-ton.
Yeah, they make a lot of them in Mexico, and San Antonio does the water cooled. We just had a Carrier chiller that it's in the, I guess the 600-ton range, and we just had it tested, and it it was a zero tolerance test, meaning there was no deviation from AR. I know that 4%, 5% slide on that, and did okay. But it lost in a couple of low ends. But overall, it's barely passing, and this chiller's about 8 months late. And so we're debating whether do we accept it or do we just we don't want to push it delays the project, so we kind of don't have a choice. But that lead time was. No one could give us a reason why. It wasn't a lack of materials. I don't know if they're just being strict with their procurement. Like their copper tubes, the Wolverine's they sell tubing to everybody. They sell it to Carrier, they sell it to York, they sell JCI and Daikin and Train. They all get from the same supplier. Everyone else is getting the same materials. It might be something because they like to keep it close to the vest. Carrier doesn't like to farm out. York, and I say York because I always know them, but York JCI makes their own compressors. They make them, they offshore them to Mexico, but a lot of them, but they They control that, and in York, PA. So they make their own coils, so they can control a lot more of their production. They make their air handlers in Hattiesburg, Mississippi. They make some of their coils in York, some of it in Hattiesburg, but they control it in-house. So they're buying their material, they're bringing it to bear. Carrier's very similar. I don't know why, what part or what component or subcomponent made that go south on them.
These are Quantec, so
Okay, yeah. I forget who Quantec is who owns that now, but that was I got mixed up with Multistack. Sorry.
well, it was a York for a while. And I'm not sure if Johnson controls his name now or not. It's who the parent company is.
Not line we spec'd in some years.
And then we're told on other products, colors the same size, 50 to 60 weeks.
Oh yeah, way over a year. Right, exactly.
What are you saying with the rooftops?
The smaller ones have gotten better, but the bigger ones can be anywhere between 20 and 40 weeks.
Yeah. Well, that's
Yeah.
rooftop, back at rooftop.
Johnson Controls does Quantec.
Johnson Controls what?
Johnson Controls does Quantec.
Oh, they do. Okay. I didn't know that. I should know that. I know the rep very well here. We never talk Quantec. I did find on one project it was a 25-ton. It was their premier line of rooftop units for a project in Rhode Island that actually had a very short lead time. It was something like 16 or 18 weeks for custom. It's just the luck of the draw. It's just how they get their stuff in. I don't know. It had a heat wheel in it. It was gas fired. It had, I think it had inverter driven compressors. It was actually a very nice unit. It wasn't cheap, but it was it had marine coatings. It's for a train station, so it had coated coils and built to last. But all that, it was still less than 20 weeks. I mean, it was just, to me, it was like almost normal, better than normal.
For a custom unit.
Yeah, exactly. They had more stuff they could deliver, more stuff that they made in-house, or more stuff they could control and bring it to the factory. So it was
Part of what we're seeing with rooftop equipment is they change so quickly to meet these DOE, EPA standards, that factory doesn't even know how to set them up sometimes.
oh, great.
And when they're trying to teach you and you ask questions, they don't know the answer to them. And I was talking to one of the vendors today and he told me he can't get answers either.
Who's that helping? Seriously.
It's a political thing.
Yeah, exactly right.
You and I know all about the money laundering.
We're trying to serve our customers. We're trying to make people, happy and comfortable. Well, gentlemen, I got to get going pretty soon. It's been a very long day for me. I apologize for just, I've been here since 6 a.m, and you know how it is. And I know, Tom, you're up as early as anyone I've known. But I'll take any questions or even offline later if you want. And but also any feedback you have on the presentation, my delivery, I can totally take some crap for that. I earn it. I'm pretty tired, but I make no excuse.
Everybody give Brad some crap now, okay?
Trying to show a ton of stuff, but anyway, I thank you all. Look forward to any comments you have, and I wish you all a wonderful and joyous holiday season.
Merry Christmas.
Merry Christmas, everybody.
Merry Christmas. Best said. Cheers all.